Okay, sorry for the delay again. We're 15 minutes late, but you guys are fast and you're good. Okay, so, I'd like to welcome Colin Broholm from Hopkins University down the road from us. Thanks for coming, Colin, and looking forward to your talk.
Hey. Morning.
Morning.
Great to see you all. I'm going to talk about quantum magnets and spin liquids. In fact, we search for a kind of new type of magnetism where the magnetism doesn't really get into a fully ordered state, but instead we have some kind of maybe an analog we could think of as an analog of superfluid helium. So some kind of quantum mechanical macroscopic wave function is going to be formed in these materials. This is something that people have been looking for quite a while, and I'd say that we're not quite there yet. But I'll give you examples of materials that are certainly very unusual and sort of on their way towards this vision of a quantum spin liquid. So I have little introductions, and then I'm going to separate my talk into two kind of main chapters. One deals with spin systems that are based on isotropic spin degrees of freedom, where it's the orbital degree of freedom has more or less been quenched, and there's just a spin which we can have do interesting things as a result of the interactions between the spins. In the second part, I will be talking about materials where there's some kind of a spin orbital degree of freedom that's been formed, and this becomes then an anisotropic form of magnetism. For both of these classes of materials, we'll be looking at insulating materials really. So the electrons are not, at least in an actual sense, moving about as itinerant entities. They're really localized degrees of freedom. The interactions are mediated by various kinds of delocalization, super-exchange interactions, where there is some kind of a virtual popping effect, but it really is mostly localized spins that we're going to be talking about. And throughout, I'm happy to take your questions. We'll hopefully have some time for questions afterwards as well. I may have too many slides, so I may be kind of skipping a little through them so we can get for lunch in time. So you had a workshop about quantum materials. I don't want to spend a long time defining what is meant by that. You probably have a sense of that. But just to say that we're interested in forming materials that have interesting behaviors as a result of quantum effects that are sort of involving multiple atoms. And I say on the mesoscopic scale, in the sense that at the atomic scale, it's always quantum mechanics, if you will, but sometimes there's a crossover taking place at a fairly short length scale where things become kind of classical. So those would be the systems that we're not particularly going to focus on here. We want the systems where the quantum mechanical wave function actually persists as the relevant entity to be thinking about in the physical properties that we're exploring. And our focus is very much on the fundamental aspects of it. And of course, we think of superconductivity, and we think about materials that have some topological character to them. What I'm going to be focusing on today are these strange magnets, very quantum mechanical magnetic systems shown down here. It's a very interesting area that connects chemistry, material science, and physics. All of it has to somehow function for us to make progress. And you've heard in this workshop about various aspects of it. This talk focuses more on the step after the material has been discovered, and we're trying to understand the underlying interesting collective phenomena in the materials. Eventually, of course, we want to make stuff that can be used in society to make life better or easier for us to and more enjoyable. And so we have various ideas for how that can happen. And the funding agencies are quite excited about this kind of area. This is a big report from 2016, so it's a little bit dated now, but in it, I was involved in developing this report, and in it you can find musings about both the fundamental and the applied aspects of quantum materials. Okay, so now let me dive a little bit into the framework for understanding the kind of physics that I'll describe in this talk. And I just want to put a nod to the theoretical side of it and indicate the background that we have to have in mind as we think about these materials. So what I've written down here is the Hubbard model, which involves electrons actually hopping on a lattice. This is the kinetic energy term, and here's then an interaction term, which is comes into play when there are more than one electron per site on this lattice. So I'm going to specifically be thinking about a case of one electron per site, and of course I'm able, while still satisfying the Pauli exclusion principle, to have 2 electrons per site. But if I round up the strength of this term especially, then those states which have 2 electrons per site become very high energy. And so then this process of an electron jumping from a site to another, and therefore forming a doubly occupied site, becomes a very high energy process. And so we're going to think about materials where that process essentially is forbidden energetically. However, we can still have a virtual hopping taking place, but this hopping can only happen if in fact, the electron states are different on these 2 sides, because for this hopping to take place, mediated by Coulomb interactions, then actually these spins have to be opposite to each other, and that then leads to a description of the low energy sector, where I have an antiferromagnetic interaction between the spins, because only when these spins are anti-parallel to each other can I have this hopping process take place. And so the low energy sector is now described as a spin-only sector, and the relevant interaction looks like this, and you can actually write it in this way. This then corresponds to essentially the low energy states are those where we have singlet formation for pairs of spins. So that's a good way to think about the quantum mechanical aspect of it. It's true, you could say, well, it seems that you want spins that are sort of anti-parallel to each other, but actually the underlying process is one that has to do with gaining energy from electron delocalization, and you gain that if you can form singlet. And so we should expect to find in these systems with which are mod insulators with odd number of electrons per with a half-fill band, we should find this kind of tendency towards singlet formation on the sides of the lattice. Yes. Yes. Sorry. This would be a vector of Pauli matrices. That is going to form the spin of this quantum group. All right, so then how are we going to look at these materials? And since they're quantum materials, we have to use quantum beams. That seems natural to us. And the quantum beam that we'll use is actually the neutron. So we'll have the neutron come into our material and probe the environment, and then come back out and reveal the information about what's going on both within the atoms and between the atoms. Essentially, what we're thinking about is a process of a neutron with certain momentum coming in, a certain scatter momentum, and in the meantime, this has been playing out, and that's okay, because what I wanted to illustrate is that we measure then the probability of scattering as a function of, oh, that was a bit too much. I'm sorry. I don't know why I'm doing that, but we're going to measure the probability of scattering as a function of wave vector transfer and energy transfer in this scattering process. You can simply think of it as a collision. Particle brings in momentum and energy, and then it can actually deposit momentum and energy in the sample. But I have to conserve momentum and energy in the scattering process. And so I have actually 2 positively different situations that can occur. I can have a single particle process in which the neutron actually creates a quasi-particle in the material, delivers its energy and momentum to this quasi-particle. In that case, I can only have scattering for a certain locus of points that form a dispersion relation for this underlying particle. I have to satisfy momentum conservation that forces the scattering to only lie in this dispersion surface. On the other hand, if I have a multi-particle process where the neutron comes in and actually creates multiple particles, then I have various ways that I can deliver a certain center of mass momentum to the collection of particles And that will typically, at a given momentum transfer, give me a whole continuum of scattering as a function of energy transfer. So by looking at the scattering cross-section that we detect in our experiment, we can actually understand whether the neutron is able to create the underlying quasi-particle individually, or whether it has to take place in this kind of multi-particle process. So there's something really qualitative that comes out by looking at the experimental data. But that's not to say that we don't fully understand the underlying mechanisms. We do, and that's one of the powers of neutron scattering. We are measuring something called a partial differential scattering cross-section, which is indicated here. And I know that tomorrow you're going to have a nice talk by Jeff Lynn, which will talk much more about neutron scattering. I'm not going to spend very much time on this, but with this slide, I simply want to end up with this expression on the bottom here, and that shows us the entity that we're actually measuring experimentally from these materials. And you'll probably see more about this tomorrow, but and some of you may have seen it, some of you might be completely surprised by this. But if you look at this part of it, then that is what we call a spin correlation function. It involves the correlation between spins at two different sites of the material at two different times. That's the thing that we can actually probe with neutron scattering, not as a function of position and time, but as a function of momentum, which is the conjugate variable to position, and energy, which is the conjugate variable to time. So when we look at these maps in wave-vector and energy space, we've from years of looking at these data, we've become familiar with kind of what does that relate, how does that relate down to this correlation function, which somehow encodes a lot of the interesting collective physics of materials. Good. That's our method. We use various scattering facilities. This is a picture from the spallation neutron source down in Oak Ridge, Tennessee. And here's a picture of an instrument at the NIST Center for Neutron Research, just on the road from here, actually, really close. There they have a wonderful set of instruments for scattering experiments, including this machine that we're using for some of these experiments. It's the so-called MAX spectrometer. And I won't get into details about how the whole thing works. Suffice it to say that we like this kind of, as experimentalists in this field, we're very excited about working on advancing the technique and all this stuff. But I'm going to mostly in this talk, we're thinking about what does the data tell us about the materials. Here's the actual place where we spend our lives, or we like to spend our lives, doing these scattering experiments. Here's the cryostat. All of the cryogenic stuff is around and underneath. Here's the 20 megawatt reactor, and underneath is the actual instrument. So it's a fairly busy place. Okay, so now let's look at some of the data. And in this talk, you're going to see quite a few of these pictures of these kind of colorful pictures. And what do they actually mean? Well, we use the color to indicate the intensity of scattering. And typically, we'll have along the horizontal and vertical axis, we'll have coordinates that characterize the scattering process. In this case, it's momentum transfer along the horizontal axis and energy transfer along the vertical axis. And momentum transfer is indexed by high symmetry points in the Brillouin zone. And so that's kind of the thumbnail image. And so let me say a few words about what we learned from this kind of data. I'll first say that the reason that I'm showing this is because I want to have a contrast to some of these very exotic quantum materials that I'll later talk about in this material. So this material is actually not so terribly exotic. It's still interesting, etc. But I want to start with something that's fairly straightforward to understand. Then we'll later see something even wilder, but we'll still be looking at these kinds of charts. Okay, so what do we see here? Well, the upper chart, well, first of all, I should say this is an experiment copper 2 oxygen selenium 03. It's a material without inversion symmetry, and it actually has a tetrahedron of copper, and there are two different kind of sites. So the three black sites are one kind, and there's another kind of copper site, which is lighted, which is light. Some look like a paracor structure, but there's a breathing character to it. So these interactions within this unit are strong. and the interactions between the units are much weaker. And that actually leads to the formation of effectively a spin degree of freedom. So these four spins together form kind of a macro spin. And this we see experimentally from these kinds of data. Namely, if you look, there's kind of two bands of excitations. The red color is higher intensity, and here's higher intensity as well. Then there's a kind of a valley of nerve scattering between 15 and 25 millielectron volt. And that indicates that all of this stuff up here is actually an intra-tetrahedral excitation. So that's when we begin to upset the low energy configuration of spins that otherwise would exist, is when we create these kinds of excitations. So I'm going to actually abstract from that, and I just want to think about the excitations that maintain this unit, its integrity in its low energy state. And so that's all of the excitations down here below 15 millielectron volts. And so we've zoomed in on those down here, and you can see that they're actually there are actually several bands, and I won't, as I said, I'm not going to spend a lot of time talking about this material, but the main thing I wanted to emphasize is that these are really sharp branches through momentum space. And that means that what we're actually exciting here are what we call magnums, which is sort of tilting the spins away from their otherwise ordered spin configuration in this low temperature state. These magnums can actually propagate through the system, and the slope of this kind of curve would indicate the velocity of propagation of those magnums. And then we can actually, from this whole dispersion relation, we can actually obtain the interactions that exist between these units within the crystal. Now, when you look in somewhat more detail, you notice that there are some regions where you have really sharp branches, and then there are other regions where things get fairly messy, and there's a really broad character to the scattering there. And this we actually understand why that happens. Oh, before I get into that, let me just I wanted to emphasize that we have the ability, really Oleg Chernyshov and Yi Lu, who were working on this, we have the ability, they have the ability to actually calculate the scattering cross section, not only location of these branches, but also the intensity of all of these branches. And this is the experiment, this is the theoretical description of it, and from it, we obtain values for all of these exchange constants in fairly significant detail. But we also see that there's certain regions where there are distinctions between the theory and the experiment. So for example, here, the theory predicts a sharp mode of excitation, but here in the data, it's really kind of become significantly broadened. And I think we know why that happens. And the reason actually is that in this particular range of energy and momentum space, it happens, and that it's actually this range here around the X point, it happens that it's possible to have a single magnet decay into two magnets. And so because of that being possible, and because of the fairly low symmetry of this structure, the magnet really cannot survive when it gets into this kind of allowed phase space for decay into twins of itself, if you will. And so the momentum and energy carried by the magnet is dispersed into two magnets. And so experimentally, we see that this branch just completely loses its coherence in this particular part of the phase space. What's shown over here to the right is the calculated dispersion relation along with the calculated phase space where we do have access to those multi-particle excitations. So here you have kind of a mixture of what I said initially. I have some modes which are coherent, and then other places in phase space, they actually decay. And in some cases, we have an understanding why that takes place. Okay, so I think that is my summary about the kind of more normal situation where the basis is an ordered magnetic state and magnet excitations, but then in some places the magnets are not, they actually decay, but it's a good initial kind of stab at it. Now I want to get into these materials that are very quantum mechanical, where there's not even an ordered state. And here's an example which is fairly straightforward to understand, which is again, the copper atoms forming this 1.5 degrees of freedom, and they form a square lattice. But rather than a square lattice of interactions, then there are actually these diagonal interactions shown with dashed lines that are quite strong in the system. In fact, those are the dominant interactions. And when that happens, there's a quite interesting kind of state that can form, which is called the Sutherland. Well, the lattice is called the Sutherland lattice. And it is a system that has an exact analytical ground state that is known, which is just a product state of singlets. So every single pair of spins which has this strong antiferromagnetic interaction actually forms the singlet state. For copper, the orbital degree of freedom is completely quenched in this kind of material, and so it's just a spin half with a fairly isotropic interaction. And when that happens, then we can classify these states according to the total spin quantum number, which for two spins can either be 0 or spin 1. Then we would expect to have basically excitations that correspond to promoting this singlet into triplet. And that should be kind of the, instead of the magnum, now becomes this kind of singlet to triplet excitation. And of course, to do an experiment, we need a material. And amazingly, this group, Kanyama et al. Some years ago, found a compound that really does form this kind of model, fairly strong interactions between spins, which are these diagonal directions, but then much weaker interactions between along these directions. So this is the strong interaction, and this interaction is much weaker. The perpendicular nature of the way these pairs present to each other is also very important, because you can say once a singlet is formed here, then this spin kind of is always seeing anti-parallel spins as this thing undergoes its quantum fluctuations. So there's a very high order, almost no impact interactions between these dimers, as we call them. Now the susceptibility for this kind of system has cured isolated at high temperature, and then as the system settles into the singlet ground state, the susceptibility just drops away completely, and you have exponentially activated susceptibility at low temperatures. And in neutron scattering, there's a sharp excitation at 3 millielectron which simply corresponds to making transitions from the singlet to the triplet. And if you look more carefully, which Bruce Colin and company did some years ago, then you find that this transition is actually split into 3 components, and that really reveals experimentally that it is in fact a triplet. And the reason that it's split is that the interaction is not ideally isotropic. There is low enough symmetry that we can have things like DM interactions, and various complexities can be there, and that can actually lift the degeneracy, which is then seen experimentally. So here's a system which at low temperatures essentially is not magnetic at all, because each pair of spins has settled down into the singlet ground state, and it's only when I, in fact, make a transition into this triplet sector that I have any magnetism at all in it. So you could ask, is that a spin liquid? And it turns out that we don't like to call it a spin liquid, because essentially there's nothing really dynamic at the collective scale in this material. Every single pair of spins is just forming a singlet, and it just basically sits there without doing very much. And so it becomes, it is maybe it should be thought of as a quantum paramagnet or something like that, but it does not really have any collective physics involved. So what do we then mean by a quantum spin liquid? And basically, what we need is to again have a coverage of the lattice by singlets, but we need, in fact, to have a superposition of many different ways of forming singlets on the lattice, and we want that to be in a quantum fluctuating state. So the ground state should be a superposition of many of these singlet coverages of the lattice. And you can ask, why do you have that distinction? Why do you feel that that's an interesting thing to look at? And really the reason is that the excitations take on a very, very different character because of the fluctuations. You see, once you promote a pair of spins from the singlet to the triplet, you form this entity with 2 spin-half degrees of freedom, which we've looked at previously, but as opposed to the Sutherland lattice, now we can actually, as the quantum fluctuations of the singlet coverage takes place, we can separate these spin degrees of freedom from each other in this way. And so now you get this kind of lone spin half degree of freedom that can wander through the lattice. And that turns out to be the fundamental quasi-particle of the system. It's no longer a Magnon excitation or a singlet to triplet excitation. It's actually the deconfined so-called spin excitations that are indicated here. And so all of the transport properties should be really very different for this kind of quantum fluctuating state compared to the quantum paramagnet that we talked about previously. So those are the kind of systems that we would like to look for. And just to show that they actually kind of do exist in the material space, then when we go to a one-dimensional version of a spin half system, which was done here by a group involving Martin Murigal and Henrik Weiner, Meksha Emily and others. They looked at copper sulfate, a high dash 5D2O, so it's a compound that has to be deuterated in order to do neutron experiments. But it has in it chains of copper spin half degrees of freedom. And that is kind of the earliest example of a quantum magnet, which was invented as a model by Hans Bethe shortly after the invention of quantum mechanics back in the 30s. In that case, it turns out that you can actually analytically calculate this dynamic correlation function that I talked about in the very beginning. And so you can actually now experimentally measure the standard cross section, and then you can theoretically calculate it and really make a direct comparison between the two. And it turns out that this spin one-dimensional chain, in fact, does form a kind of a spin liquid in the sense that there are fluctuations of the singlet coverage involved. And therefore, the excitations are actually spin-like excitations, which are deconfined spin half degrees of freedom. And therefore, the standard cross-section has actually a continuum in it. So this is the experimental data. And this is momentum transfer. I think some momentum transfer. And then there's actually a whole range of energy transfer where I do see scattering take place. So that's the experimental indication of deconfinement. It's at very low temperature, so it's not a thermal effect. It really is a quantum mechanical effect. It really shows that the neutron is scattering through a multi-particle process. And then this is really bolstered by the theoretical calculation of that cross-section. Here's a beautiful comparison of the experimental measurement function of energy transfer, and it really, the points of the black ones, the red line is an analytical calculation of the full cross-section of spin half chain. It really accounts for the data. It's a pretty amazing accomplishment. Good. So then, let me say a few words about the spin one case. So you might ask, this is quantum mechanics. What happens then if I change the spin half to a spin one? And this was taught to us by Duncan Haldane long before the experimental world kind of caught up with it. He told us that there was going to be a gap in the magnetic excitation spectrum if you change spin half to spin one. And for many years, people were not didn't understand, I think, really what was being talked about, and the way it was described was fairly difficult to follow. But this is now completely accepted and understood and shown experimentally and theoretically. And the Nobel Prize was awarded to Duncan Haldane. And in this beautiful book, this diploma, that's probably not the right name, but this beautiful sort of written version of the Nobel Prize, there's also a picture of the spin one chain, which actually very nicely illustrates what is the ground state for the spin one chain. Now, just verbally kind of state what happens in this case, which is that now the spin one degree of freedom is actually this little yellow thing, and it is composed of two spin half degrees of freedom, right? Because there are two holes in nickel 3d8. These two holes conspire to form a spin one degree of freedom. But the way it's described conveniently in this work is we think about these two spin half degrees of freedom kind of individually initially. And now at each side I have two spin half degrees of freedom, and I have two nearest neighbors So what's more natural than just to form a singlet between the neighboring spin 1/2 degrees of freedom? And this I can actually do in two different ways, if you will, but it becomes symmetrically related to each other. So I end up not needing, in fact, to break the symmetry in any way as I form this so-called valence bond solid state of the spin 1 chain. So excitations from this kind of state should then correspond to breaking this singlet into its spin 1/2 components, and then I can actually have that kind of move along the spin chain. So we would expect that this should cost some energy, and so that there should be a gap in the excitation spectrum, something you didn't have for the spin 1/2 chain. There was a sequence of experiments done by many different groups that saw in various materials the presence of this unusual gap in the excitation spectrum for the spin 1 chain systems. And here are experiments that I was involved in on a spin 1 nickel-based material, yttrium barium nickel oxide. And you can see really a very significant qualitative difference between the excitation spectrum for the spin 1/2 chain that I showed previously, where there was a broad continuum of scattering, and it was actually gapless, reached all the way down to 0 energy. In this case, this is 0, but there are no excitations down here because it costs a certain energy to actually create this triplet. And then you also see that at any given momentum transfer, there's a really nice sharp mode of excitation in the system. And so here's a case of, if you will, Magnum-like mode of excitation, which is, people think of it as having confined spin excitations. And I want you to keep this in mind for a little bit later in the talk. I'll have another case which you think may be related to this, but in higher dimensions. So that'll be the next. The next idea is that we are now going to move out of 1 dimension, and we want to go to 2 to 3 dimension, and still find this kind of collective quantum magnetism. And then you have to go to some fairly esoteric lattices to basically stave off or hold off the otherwise tendency that would exist towards the development of a long-range order of magnetism. So once I have some kind of phase transition into a long-range ordered antiferromagnetic state, then I've left the space of the quantum spin liquid, which I'm looking for. And so we come to lattices like the triangular lattice, hardcore lattice, where you have this kind of triangular motif that shows up. Why? Because that will preclude really an anti-alignment of all of the near neighbor spins. There's just no way that you can actually do that when you have these triangular degrees of freedom. So that frustrates the development otherwise of the long-range magnetic order. So we'll be focusing on those kind of lattices. And of course, the first one to think about was the triangular lattice. And in fact, back in the 50s, late 50s, Anderson, P.W. Anderson, Nobel laureate, was noticed or indicated, showed in his paper that there was actually a fairly competitive low energy state that you could form amongst spin 1/2 degrees of freedom on a triangular lattice, ended up being quite competitive compared to a long-range ordered state. So in other words, this kind of so-called resonating valence bond state of singlets that are kind of rearranging themselves on the lattice, as I've indicated on an earlier slide, that kind of state can be shown to be fairly low energy as well for the triangular lattice. So this is pointed out in this paper. Then later, by various methods, including exact ionization studies, it was shown that, in fact, the ideal Heisenberg case of spin 1/2 degrees of freedom on the triangular lattice, in fact, does have long-range magnetic order. It's a little bit disappointing in a sense, certainly not inconsistent with what Phil Anderson had said, because it is a low-energy state, but it turns out that for the kind of simplest version of a triangular lattice with antiferromagnetic interactions between spin 1/2, then in fact you do have long-range magnetic order, as indicated here, that there's a finite stack of magnetization, even in the limit of spins going, even in the limit where I have an infinite number of spin degrees of freedom. Okay, so but still that hasn't held people back from thinking about the possibility of some kind of spin liquid physics on the triangular lattice. And in fact, there are a number of materials, including these organic magnetic systems. And here's the particular example where you have spin half degrees of freedom on the lattice. This is actually NMR experiments that you all prepared for that from the previous talk. And what you see is that as you cool down this material, there's no anomaly that would indicate a phase transition. The material continues to behave as it does at higher temperatures. And so this is kind of an indication that this is not a normal ordered state that's developing in this case. And there are other examples of materials, triangle lattices, spin half, that have really interesting magnetic properties. And I think it's recognized now that various kinds of, you could say, imperfections in the way materials realize the triangle lattice could actually cause really interesting behaviors that are not seen in the simplest version. And in fact, all of this concept of having a resonating valence bond state nearby to be relevant for many of the materials that people like to look at. Here's a compound that Colin and his postdoc developed, which is quite an interesting idea. So he knew that the triangular lattice was interesting, but then he said, why not put something else than a single atom spin on each side of my triangular lattice? So instead of putting this one atom with spin half, he put a little kind of stick of, in fact, 3 iridium atoms. And since each of those are a spin 1/2 degree of freedom, we actually can't end up, sorry, I need a bit more than that, but it turned out that we end up with a spin 1/2 degree of freedom per site. But it's now some more complicated entity, actually. And so the idea is that maybe that would promote this resonating valence bond state. And lo and behold, this material does not have a phase transition to long-range order. It is a crystalline material. It is an ordered material. However, it doesn't actually have a phase transition. So this is a really promising potential candidate for spin liquid. And this is kind of where it stands right now, because there are some challenges associated with looking at these iridium-based materials. Okay. Now, there's a lot of interesting work that's been going on over the last, I think maybe three or 4 years, including on these kinds of phosphite materials that involve a rare earth atom on a triangular lattice. So these are actually fairly well-ordered systems, it seems, and I think it's still kind of in development. Some of them do have magnetic ordered phases. Other, when you cool them down, do not develop a long-range magnetic order. All of them, as far as I know, have a excitation spectrum which does not look like the first material that I showed. It doesn't have like magma excitations in it at all. It actually has, this is the experimental result, a very broad kind of continuum of scattering, looking quite a bit like the spin half chain. And then compared here with various very sophisticated theoretical calculations of the dynamic correlation function. So it's, you know, the kind of work that's being done here is a little bit akin to, or is akin to what I suggested for the spin half chain. However, in this case, it's much harder theoretically to calculate the dynamic correlation function. And so this is still kind of in development. I think this is really interesting, interesting work. Okay, so now I think I want to actually, since I can see that I'm a little, I'll be otherwise going over time, I think I would like to jump forward a little bit. So now I'm worried about my, okay, I'm gonna, okay, I don't have my, worry that I may, if I stop it, I will stop it, we'll see what happens. I tried to stop it, because I just want to jump forward to another slide. But this may cause some tremendous, okay, here we go. So I'm going to skip the next little section, and I want to come to talk a little bit about these anisotropic systems. I think that's the most different from what I've talked about so far. And so let me jump into this section. Okay. All right. So here we're going to think about spin orbital degrees of freedom. So there will be both spin and orbits involved. And the main consequence that's relevant here, that wasn't what I had to find, but I think it's the main consequence that then happens is that these super exchange interactions now will depend on the orientation of this spin orbital degree of freedom. You can think about it like this, that for the purely spin degree of freedom, then the exchange interactions, which are defined by overlap intervals, there's a certain super exchange path, I think about the overlap intervals, all of those intervals only involve the charge degrees of freedom, and they don't actually, to lowest order, if I forget about spin orbit interaction, involve the direction of the spin. So my interaction becomes fairly isotropic. But once I form a spin orbital degree of freedom, then as the direction of the spin orbital entity changes, then the whole charge distribution changes as well. And that actually leads to a spatially anisotropic interaction between the spins. So something we didn't have at all in the previous problems that I was looking at. There we just had like S1 dot S2, and that was it. It's an isotropic term. So in the past, we actually kind of, I think, tried to avoid looking at these kinds of systems because it was just the complexity was too high. And we thought that there was a bigger chance of finding interesting physics if we had an isotropic degree of freedom. But then there was actually the discovery quite now more than a decade ago by Alexei Kitaev of an exactly solvable model that did involve anisotropic interactions. In fact, it involved the honeycomb lattice in which each spin degree of freedom, which of course has three Cartesian directions, x, y, and z, but it actually has a situation in which only the x component is involved in the interaction along the green bonds, and only the y component is involved in the interaction along the blue bonds, only the z component for the red bonds. This is a completely different kind of highly anisotropic interaction that's present there. It was developed, as a somewhat, it seemed like a rather esoteric model, and it was, of course, I don't know exactly how it came about, if you will, but it turns out that when you do that, it's actually possible to show exactly by decomposition of the spin degree of freedom into Majorana fermions, it's possible to actually develop the exact ground state for this kind of model with this particular anisotropic interaction. So that was hugely important for the field because it gave a specific example of an exactly solvable model that would have a spin liquid ground state with many of the features that we know are associated with the quantum spin liquid vector. It's called a fractionalization and a lot of interesting transport properties, etc. So then you ask yourself, can you find material that realizes this kind of thing? And that was then addressed by the community, I guess, of the past decades, and there are various very important papers, including Colin and Jacqueline's contribution, where they show that there is a way that you can actually do this, and it involves using the spin orbital degree of freedom in this case actually in a 4D 5D electrode system, which is based on iridium, and so you can form this effectively spin half degree of freedom, which is now the spin orbital entity. So it has, when you orient the spin, that there's a certain charge distribution which comes along with that, if you will, and this does give rise to a anisotropic interaction, which might then eventually lead to some spin liquid type ground state, which is related to the exactly solvable model. So there's been a huge amount of work on this, and we also did some work, and I'm going to just show like a couple of pictures. First, I should say my collaborators in this work are shown on this graph, particularly Tom Halloran has been working on this somewhat quietly because it's been fairly complicated, but the papers are about to come out now. And we've been working on on two different materials. One material, which is the beta lithium pyridate. This is an interesting situation. We have to use two different isotopes to do good neutron experiments. These, like NMR, neutrons are interacting with the nucleus, and some nuclei are not healthy for us. I mean, they actually are not the biological aspect of it, but they may gobble up the neutrons. They don't come out at all. So we need to pick the right nucleus, which means lithium-7 instead of lithium-6, and 193 is a bit better for iridium. And we picked this compound, which actually is magnetically ordered. You can say, well, why did you pick that one? You were looking for a spin liquid. It's because we wanted to get our bearings by looking at a more normal compound initially. And it turns out that there are lots of challenges. We cannot actually make big enough single crystals for this work, so we have to do it on a powder sample. There's a powder sample here, and this is the kind of thing that you then make. Still wave vector transfer, energy transfer, but you don't have directionality to wave vector in this case because it's a powder sample. And so all you can get to see is this kind of little blob. But we were still very excited being able to actually couple to the magnetism, and still, because we know exactly what the interaction cross-section is, we can make a fairly specific comparison to various kinds of models of interacting spins. And we were able to obtain, I think, fairly reliable estimates for these parts of the exchange matrix. Because now I have an anisotropic interaction, so it's not an exchange constant, it's actually a whole matrix that you have to pick out. And we were able to get these kinds of parameters. Then the next step was to take a iridium-based compound that actually has some kind of a spin liquid state in the sense that it doesn't have an ordered magnetic state. And this is so-called, we call it the Takagi compound, which is a case where there's where you actually replace some of the lithium by deuterium, which actually sits in between here. That gives rise to some disorder in the system, which you certainly have to worry about this. But it does give rise to a material that doesn't have a phase transition, has quite interesting low temperature specific heat behaviors. So this may in fact be some kind of a spin liquid. And so we tried to look at that with neutrons, and it's really tough. I don't know if you want to be dissuaded from doing neutron experiments on your sample. This is just about the hardest case one can have. We have to use 3 different isotopes. The iridium, the lithium, and the deuterium instead of hydrogen. And what you end up seeing is a small region in momentum space down here with a very kind of diffuse contribution to the intensity. It's quite different actually from the case of the ordered magnet. So we really can see it like a distinction between the ordered system with anisotropic interactions, gap in the excitation spectrum as we expect for the ordered system. But in this quantum spin liquid candidate, consistent with the power law, specific heat, etc., we do have what seems to be a gapless excitation spectrum, and we can measure the momentum and energy dependence of that. Clearly not at the, there's not that much information to get from these kinds of data. And there's another kind of challenge, which is it turns out that the θH spin liquid, in the ideal case, you can actually calculate the dynamic correlation function, and it's extremely bland. It has this kind of very broad features in momentum energy space. And therein lies the interest, if you will, because that is what I said in the very beginning. Magnums will give you these sharp trajectories, but fractionalized quasi-particles will give you a broad continuum of scattering. And so the data we have is kind of at a qualitative level consistent with that, but it's also consistent with various other things because of the spherical averaging inherent to a power sample. So now I think I'm running a bit short and I'm running out of time. And so I just want to end by, I would like to briefly show you this, but I won't go on for long. I just want to say that because of the complexities of the iridium materials, we thought let's look at cobalt instead, because cobalt actually can also form an effective anisotropic spin-half degree of freedom and may be able to form this kind of θF state. And so we, with Pava actually, and then Brigham Zong published, I think, the first kind of modern or recent paper on this barren polarsonite compound, which has this structure. It has a honeycomb structure. It has the same kind of 6-hole coordination that Jacqueline pointed out could give rise to theta type physics. And so this compound may have this kind of thing going on. But what we found in our work, and the paper is on arXiv, was actually that, that there is interesting physics in this material, but rather I think that the theta type frustration is actually a frustration that arises out of multi-range exchange interactions. So I just want to leave that message. So the theta type model is one in which a spin that I'm pointing to here has its three Cartesian components interacting with three neighboring sites, and therein lies the frustration. If it's going to satisfy one of these interactions, then the other Cartesian component will not be able to come into play. So I have kind of a local frustration associated with this unit. But what we find in the cobalt material is that what instead is playing a role is a multi-range competition. So it's a competing multi-range interaction. So I do have near-neighbor interactions which are in fact fairly isotropic. And then I have a longer range interaction to this point, and both of those, these cannot simultaneously be satisfied. So it's actually a competing first and third near-neighbor interaction, which seems to be relevant in this material. And we were able to deduce that in a collaboration actually with the Youngbeck Kim's group from Toronto, where we analyzed with them a fairly detailed measurement of the field-dependent excitation spectrum of this material. And you can see actually here, sorry, let me just go back. What happened? Oh no, here. And I just want to show, this is in the low temperature state of zero field. And this is actually has a lot of interesting features in this excitation spectrum, both sharp branches and very intense continua of scattering, maybe indicating the proximity to some kind of a spin liquid state. But then as you apply a field and drive it into a ferromagnetically polarized state, all of the complexity essentially goes away, and you end up with a fairly sharp load of excitation, just a ferromagnetic load of excitation. It was by analyzing this entire set of data that we were able to actually obtain, I think, fairly reliable determination of the entire exchange tensor, because now you have instead of just a dot product of spin, there's a whole matrix that lives in here, and that has to be determined experimentally, which we did. Good. So then I just want to summarize, which is to say that we've been looking for quantum spin liquids. We certainly have found in this work, and work done by a large group of scientists interested in this direction, and certainly have found that the kind of the standard description of a long-range ordered antiferromagnet with magnet excitation works sometimes, but really there are many complexities that come in, including damping of magnets and also partial fractionalization in some limited range of energy. Features that are better understood, perhaps coming from the spin liquid side of it. However, there's not really a compound we can point to now, I think, where we are all in agreement that this is the quantum spin liquid with all of the features, apart from maybe in one dimension, but in higher dimensions, it's still very, very active, and I think interesting area of research involving, as we said, chemistry, material science, physics, and I think many of us are hopeful that there is progress, and we're going to get there. Okay, thank you for your attention, and I talk to you.
Can you expand a little more on how you get Majorana's and quantum spin liquid?
I'm not sure I'm very prepared for that. Here. Yeah. So yeah, I mean, I think I'm not really well prepared for this, but essentially you need to break down the spin into all of these components, some of which are in fact Majorana families, and then when you rewrite the exchange interaction between the spins, which is the thing that's happening in quantum chemistry, if you will, then out comes a becomes a product term of ironic diamonds that actually can be driven into its low energy configuration. And so that becomes the ground state. And you end up actually with a gapless excitation spectrum overall, but a gap in the spin sector of the excitation spectrum. And this all works very well when you only have the the so-called ketone interaction. And in that limit, many things can actually be calculated, including the dynamic correlation function. Once you throw in other terms of interaction, then basically you have to sort of perturb away from the ketone ground state, and it becomes a lot more complicated. But I think that therein lies a lot of the challenges experimentally now, is that we can measure stuff to some extent, that to really reach the strong conclusion based on measuring the dynamic correlation function, we need to have the theoretical machinery come along with it. And that's the challenge right now. I think it's being addressed, but we're not quite there yet.
Thank you.
In your tale, it sounded like this cobalt compound is sort of unique in having this very large or sizable sword neighbor interaction. But as far as I recall, it's been the case in all these compounds, in iridescent, also in ruthenium trichloride, and essentially this interaction is the one that drives zigzag order in many of them. And moreover, it's sort of like legacy of this molecular orbital that formed in non-relativistic case. So why do you think that this cobalt stands out in this?
I think I would agree. Actually, I mean, it's really the theoretical model that one can make progress on is the one with the near-neighbor interactions, and so that becomes very much in focus. But as soon as we dive more into the actual materials, we find that all interactions that are allowed and kind of present, and it's really a quantitative question how strong they are and whether they have qualitative impacts. So usually in the beginning of the projects, the experimentalists will focus on the simplest possible model. In this case, likewise, we were focusing on the anisotropic near-neighbor interactions, but as we progressed in having more detailed experiments, etc., it was quite clear that the third neighbor interactions was absolutely critical to the underlying physics. So that was kind of the what we noticed. But I would, in hindsight, say that we should have expected this term should be present.
Yeah.
Can you comment about, let's say, the role of, broadly speaking, material quality in your experiments and the kind of back and forth you have with the developers?
Yes. So it's hugely important, and in the interaction between the chemistry and solid state chemistry and materials science side, I think it's really very exciting and extremely important. The main problem that I see, basically in the scattering experiments, is that we would like to make this kind of distinction that I was showing you here. We would like to look at scattering cross section, and then we'd like to say, well, is it a single particle process or multi-particle process? And those kinds of qualitative conclusions are really useful because they don't require us to have the full theoretical calculation of the dynamic correlation function. However, if there is disorder in the material, then all of this really breaks down, because once there's disorder, then you don't have a translational symmetry, and then you don't have momentum conservation. And all of this was built on momentum conservation. So once you put in disorder, you should expect all of this to become filled up. There should now be excitations at all momenta, and so you're really measuring some kind of a mixture of the response of the periodic system with some kind of a density of states of magnetic excitation. We can really see that experimentally as the quality degrades. Basically, all of these regions that should be empty now begin to fill up, and it's not because of damping of the nodes. It's really because of loss of momentum conservation. The particle magnet comes in and it scatters from some localized object, which is the disorder in the structure. So it's really important to know, the quality, and to advance the quality of the materials. and also to really know the quality of the materials. So, for example, this work, I think that a very important challenge that lies in this work on these compounds is really understanding how well are these actually ordered, crystallographically. Is it really a properly ordered structure? Because any disorder could actually lead to these kinds of broadenings, even without interesting collective still liquid-like physics. So that's really the key challenge to address, and it makes it all exciting. I think. Yes.
Front first, and then
I have a question about this slide, actually. So your phase diagram on the bottom left.
By the way, it's not mine.
Well, are the most interesting physical properties to be found in the quantum spin liquid regime or in the critical regime, kind of between phases?
I mean, I think that's really a matter of taste and so on, and eventually I think all of it is very important. Personally, when I'm looking at a phase diagram, I would like to visit each of the phases, and then as the next step, I'm going to look at the intervening regimes and so on. So that would be my choice, but you can't really make that choice. You get whatever material there is. Very often the materials end up being somehow influenced by both phases, and then you are in this kind of quantum critical regime.
So quick follow-up, yeah. In this situation, are the emergent or excitations in the critical regime different than what you would find in say a heavy fermion compound, where you have a different it's like a quantum paraelectric, I guess, on the far end, or not a quantum spin liquid. Does that make sense?
Are they different? Oh, you're saying, is this fluid kind of different depending on what state I have it?
No, so I'm having trouble articulating. I'll ask you later.
Okay.
I was going to say that quantum critical just refers to a zero temperature phase transition between two different ordered states. So in this case, we're going from one kind of ordered state with disordered quantum spin. That's one. In heavy fermion, you go from antiferromagnetic usually to a heavy fermion state. That's more involving more conduction electrons. We're not really involved in conduction electrons, this kind of stuff. But I guess, sorry, I'm going to show here, but is there any update on the terbium manganese gallium oxide? I remember there was the role of disorder in that.
Yeah.
So have there been any further work on that and getting the sample quality to work? Or is it just like
that's one of the cases where you just will have this off-site disorder because of the character of the discharge conservation sense. So you will have magnesium and gallium that will be mixed actually. And of course, initially when you look at this structure, you would say, well, this is kind of away from the magnetic side, so maybe it's not so important. But then you begin to think about why is it that I'm allowed to say that there's no dissociative reinteraction. That has to do with the presence of inversion centers and mirror planes, etc., on the bond. And then you'd say, well, I'm looking at my best image of the structure, and it looks as if I do have some high symmetries on the bond. And so there's a tendency to say, well, then maybe the interactions maybe I can still use those things, but in fact you cannot. Once you have anti-site disorder, all of this normal symmetry arguments just fall away completely. And now all of these interactions basically will come out of the woodwork. So we should be expecting even off-site disorder, I think, should be expected to have fairly strong impacts on the symmetry of the interaction. They're only Heisenberg-like as a result of the high symmetries of the periodic crystalline structure. So I think the gallium thing is just understood to be heavily disordered. It's not to say that it's not interesting, maybe, but we have to consider the disorder as the zeroth order component.
So one last question.
I just asked is, you talked about your copper sulfide sample. There was a D2 mode term with a heat transfer, and I wanted to know why that has to be added.
Oh yeah. So the crystal structure has the like hydrate of copper sulfate. There are several of those, but the particular one used here is where there's 5 D2O, and that's part of making it into a one-dimensional system. It's kind of the stuff that fills up space between the chains. So you just have to have these 5 water molecules sitting in there. And then it just happens that neutrons scatter very, very strongly from single protons. It's an 80 bond scattering cross-section, but deuterium, it's a much, much smaller cross-section. Still has a fairly large inherent cross-section, but it's maybe 50 times smaller or so. And so if you use hydrogen in that position, you become completely overwhelmed by the nuclear scatter protons. Replace it with deuterium, and then it kind of now become dominated by magnetic.
There are like different systems which don't require that, or do you do that?
Yeah, there are, but there's a material, potassium copper trifluoride. That's a fully kind of organic compound. Well, it has no hydrogen in there, potassium, copper, and fluorine. And in that case, the one-dimensionality comes in because of the orbital ordering of the structure. So that's really a beautiful example. However, the interactions between chains is still fairly significant. So it ends up eventually forming an ordered state in those.
Okay, let's thank Colin. Let's go.